Hello, Calculus 1 students. Let's end the semester really preparing for Calculus 2, where the most important inverse trig function is the inverse tangent. You will see this show up many times in Calculus 2, and so it's worth spending some time talking about this right now. Well, before I do, what is the tangent? This is what we need to discuss. So the tangent of x, this is the sine divided by the cosine. And in particular, the tangent is undefined anytime the cosine is 0. And this happens at minus pi over 2, pi over 2. This would be 3 pi over 2, minus 3 pi over 2, etc. These x values are not in the domain of the tangent. Maybe I should write, this is the tangent. So y equals the tangent of x. Very nice. Now, an inverse function, in words, we interchange x and y. And looking at this graph, we would just flip it along the line y equals x. But the issue is that the tangent, it does not pass the horizontal line test. What this means, well, okay, you see all of these, in fact, any horizontal line hits the graph of the tangent infinitely many times. So when you flip along the line y equals x, that graph would fail the vertical line test, meaning not a function. I will say on its natural domain, we do not have an inverse function. Well, the story is not over. Fortunately, we have a convention. So what we can do is only look at this piece right here, which I've highlighted in yellow. So we restrict the domain of the tangent to is this open minus pi over 2 to pi over 2. Now, on this part, you see, passes the horizontal line test. If you flip this graph along the line y equals x, well, it will look something like this. And this will be a function. In fact, that is the inverse tangent. Well, maybe before I write the definition, let's talk about the domain and range, because this can help us. Okay, the domain of an inverse function is always the range of the original function. We interchange x and y. The domain of the inverse tangent, well, we can see here, minus infinity to infinity. It's the range of what I have highlighted in yellow. Minus infinity to infinity. These are values of tangents. And the range, well, this is the domain of what I have highlighted in yellow, which is open, minus pi over 2 to pi over 2. Now we can write down in words what this function is. So the domain consists of values of tangent. Okay, tan inverse of x equals, here are the angles. So this would be the angle between, I should call it theta, between minus pi over 2 and pi over 2 with the tangent of theta equals x. This is the definition of the inverse tangent. So let's do a few examples, just evaluating this function. Tan inverse of 0. Okay. Remember, maybe I'll write this again, that the tangent is sine over cosine. This can help us. Now, we're saying the tangent is 0. The only time a fraction is 0 is when the numerator is. So this is the sine is 0. and the angle is between minus pi over 2 and pi over 2. So this is 0. Tan inverse of 1 and minus 1, we can kind of think about the same. I'll start with this one. This says that sine and cosine are equal. Sine and cosine are equal. And the angle sits between minus pi over 2 and pi over 2. This happens here, pi over 4. The tan inverse of 1 is pi over 4. Now, similarly, this part, it says that sine and cosine, well, at least in absolute value, are equal, but they have opposite signs. So don't forget, the angle is between minus pi over 2 and pi over 2. So this will be here, minus pi over 4. Now, finally, square root 3. So we think about the angles that we know, and sine is in the numerator. So I could do a little bit of side work underneath. This would say that the sine would be square root 3 over 2. And the cosine would be 1/2. Sine theta is square root 3 over 2. This happens at pi over 3. This is my answer here. Pi over 3. Now, that was some practice evaluating, but let's think about the graph. So if we go back to this first page, remember what I said. This is always how you get an inverse function. We take this, highlighted in yellow. We flip it along the line y equals x. That's the interchanging x and y. Okay. This is the graph of the tan inverse. Maybe I will write this below. This is y equals tan inverse of x. We can certainly see its domain and range, which we thought about on this last page by looking at the graph. Now, some important limits. So you want to put stars around these. Really, as I mentioned, I'm preparing you for Calculus 2. Calculus 2, you have a lot more limit calculations than you do in Calculus 1. So we can look at the graph and see this. As x grows without bound, tan inverse of x approaches pi over 2. And similarly, as x decreases without bound, we see the tan inverse of x approaches minus pi over 2. Here are some examples practicing evaluating limits. The first one, well, we see the tan inverse on the inside of this natural log. Moreover, natural log is a continuous function with pi over 2 in its domain. So we may bring the limit inside the continuous function. This would be ln of the limit as x approaches infinity, tan inverse of x. Now this limit we just talked about, and as I mentioned, it will come up a lot in Calculus 2. This is ln of pi over 2. I'll leave it like this. Exact answer. Next one. Well, this is another properties of limits question. The numerator is approaching, maybe I'll write this as side work. The numerator is approaching pi over 2. The denominator, well, 1 over t goes to 0. So the denominator approaches 2. Okay, let's move this around slightly. Therefore, the quotient, well, this approaches pi over 2 divided by 2, which is pi over 4. Once again, I'll leave it like this. This is an exact answer. This also was properties of limits. Last one on this page, we want to limit as y approaches 0, tan inverse of y divided by e to the 3y. Well, this function is continuous at 0, so we can just evaluate. We get tan inverse of 0 divided by e to the 0. Tan inverse of 0 is 0. That we calculated, but you could also think about it again. The tangent value is 0, and the angle is between minus pi over 2 and pi over 2. This happens at theta equals 0. Okay, e to the 0 is 1. And so altogether, this limit is 0. Next, we talked about limits involving the inverse tangent. Now let's talk about the derivative of the inverse tangent. So you could justify this using, say, inverse function theorem or the chain rule and some trigonometry identities, but I'll just tell you what this is. So the derivative of the tan inverse, it's 1 over 1 plus x squared. Really, I'm interested in down here a useful antiderivative because I'm preparing you for calculus 2, and we have a lot of integration in calculus 2, but this is definitely the case. The derivative of the tan inverse is 1 over 1 plus x squared. Okay, so here's just an example where you can use that. I think this came off an old calculus 1 final. We do not simplify, practice taking the derivative. Well, first thing I'll notice is I have a product rule. Here's my first, and here's my second. The g prime, we have first, which is the square root of x over 2 times. Well, when I go to take the derivative of the second, this is chain rule. You see, I have this inside function of x squared. So first, we take derivative of the outside. The derivative of the tan inverse goes like this. Evaluated at the inside, so I put in the entire inside function. And then multiply by derivative of the inside function, it would be here. So this part is the derivative of tan inverse of x squared, chain rule. Okay, so what do we have so far? First, derivative of the second, and then plus the second times, well, the derivative of the first, this is, maybe I'll write it down here as side work. This is 1/2 times x to the 1/2. So I would get 1/4 x to the minus 1/2. And let's write this here. This is my answer, and I did not simplify as directed. Now, as I mentioned, I'm preparing you for calculus 2, trying to, and so my interest is in antiderivative. So let's look at this equation, and you could tell me an antiderivative by looking at this. Okay, what does it say? Well, it says the following. If we integrate 1 over 1 plus x squared dx, we get the tan inverse. And don't forget plus c. So this is very, very useful. It will come up in partial fractions, and it will come up, well, a variety of places in calculus 2, but in particular, we see this quite often in partial fractions. All right, now, let's practice using this antiderivative, practice integrating, and I have a number of problems we will work here. Okay, what do we need to do in this first one? I guess the first step, we want to rewrite. So this is 2y to the minus 1/2. And then I'll just recopy this. Well, the first term is power rule. So write down the 2. We add a power, divide by the higher power. The next one, we have 3, tan inverse of y. Personally, I don't like to leave fractions in the denominator, so I will rewrite this. Altogether, I have 4 square root of y minus 3 tan inverse of y, plus c. Next one. Well, what are we going to do here? Okay. We see a function, tan inverse of x. Remember the derivative of tan inverse x is 1 over 1 plus x squared. So if you want, you can rewrite this as follows. This is the integral. Here's tan inverse of x. And then times, here's the derivative. 1 plus x squared dx. This will be substitution because we have, well, we don't necessarily see it on the inside, but we do have the tan inverse and we have its derivative in our integrand. So u is the tan inverse of x. Du, we take the derivative. 1 over 1 plus x squared dx. So my integral becomes the integral of u du. We integrate, we have u squared over 2 plus c. Finally, we go back to x. So we have tan inverse of x squared over 2 plus c. Now be careful. This is the final answer. It is not the case that tan inverse of x squared is tan to the minus 2. It's not an exponent. It's an inverse trig function. And some textbooks call this the arctangent because they don't want people to think it's a power, but this is not a power. It's an inverse trig function. So we leave our answer like this. Tan inverse of x squared over 2. Next one comes with a hint. Well, if I didn't have the hint, I might be a little stumped as to what to do. So let's get started writing our hint. We use the hint. We have the following integral. We have e to the x over 1 plus e to the x squared dx. Now, you see I'm in really good shape because inside function, e to the x, and I have exactly its derivative. The derivative of e to the x is e to the x. Substitution. Here we go. Okay, u is e to the x. Du, we take the derivative. We have e to the x dx. Put this in a box. My integral of u is as follows. We have an integral. We have 1 over 1 plus u squared du. This is tan inverse of u plus c. Okay, let's do this. Tan inverse of u plus c. Final step, go back to x. Tan inverse of e to the x plus c. This is a fun one. Next question, we want to solve this initial value problem. Differential equations. This one is separable, and we have this initial condition. Very nice. So what we do, we have 1 over y squared dy equals 1 over 1 plus x squared dx. Now we integrate. Maybe I will do my integration symbol in black, like this. Okay, you see how the tan inverse is going to come into this problem? Because 1 over 1 plus x squared has antiderivative, tan inverse of x. I will put the plus c on this side. Here, this is y to the minus 2, so we get minus y to the, I'll write it like this, minus 1 over y. Y to the minus 1 over minus 1, which is exactly this. Okay, great. Well, now we need to solve for y, so I can multiply through by a negative sign and divide. So this will be minus 1 divided by tan inverse of x plus c. I evaluate at 0, I get minus 1 over tan inverse of 0 plus c, and I want this to equal 1/2. Now, tan inverse of 0 is 0, so we can recopy. Minus 1 over c is 1/2. You see, this gives us that the constant is -2. All right, I'm ready for my final answer. Y is minus 1 over tan inverse of x minus 2. The last question is a definite integral. You notice we have touched on many of the topics of Calculus 1 and seen the tan inverse appearing as we work through this lesson. So here's the last one, definite integral. Okay, it's not directly a substitution. You might think, and one place we look for an inside function is in the denominator, but you see if you tried, u is 1 plus x squared, du, this is 2x dx. And if you look at the entire numerator, 1 plus x is not a multiple of 2x dx. Well, what we can do here is definitely something we've practiced this semester. We can break this into a sum of two integrals. One will involve an inverse tangent when we integrate, and one will be substitution. So let's do this now. So this would be an integral from 0 to 1 of 1 over 1 plus x squared dx plus an integral from 0 to 1 of x over 1 plus x squared dx. Now, okay, it's just this one. That will be the substitution. In fact, I have it here. I will change it to black. Now, if u is 1 plus x squared, du, 2x dx, and I have x dx, we notice that x dx, this is 1/2 du. Now, I am a change by limits of integration kind of person, so x ranges from 0 to 1. So u, when x is 0, u is 1 plus 0. When x is 1, u is 1 plus 1. Okay, great. Oh, this would be all of my substitution box. Now the first one, here, I can go ahead and integrate. I don't need substitution. This is the tan inverse. So let's write that. The first one is tan inverse of x. And we evaluate between 0 and 1. But the second integral, this will be my integral of u. 1 to 2 of 1 over u times 1/2 du. Okay, tan inverse of 1 minus tan inverse of 0. We're going to have to evaluate both of these. Then we can integrate here. This will be 1/2 ln absolute value of u. And then we evaluate between 1 and 2. Tan inverse of 1. Let's talk about it again. This says sine and cosine are equal. So sine over cosine is 1. Sine and cosine are equal. And the angle is between minus pi over 2 and pi over 2. This is here, pi over 4. We have pi over 4. Tan inverse of 0 is 0. Then we have ln 1/2 ln 2 minus 1/2 ln 1. Now this simplifies slightly. Natural log of 1 is 0. So we are left with our final answer, pi over 4 plus 1/2 natural log of 2. So this lesson was kind of a whirlwind through many concepts of calculus, but all focused on exercises where we see the inverse tangent. I do have a whole other video in my Calculus 1 playlist talking about some of the other inverse trig functions, but this one is most important in Calculus 2. So I hope this was helpful. Thank you so much, students.